Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to analyze or see efficiency calculations. How we can calculate the efficiency of my transformer. So let's see. In generally, efficiency is equals to output upon output plus losses, or simply output by input. Output by output plus losses. This can be written as, what is the power output of transformer? EI cos pi upon EI cos pi plus iron losses plus copper losses. This is the efficiency formula. Of course, this can be written as EI nothing but kVA. kVA into cos pi nothing but power factor upon kVA into power factor plus iron losses plus copper losses. Iron losses plus copper losses. What is copper losses? Copper losses nothing but I square R losses. This is what the efficiency at full load. For example, I want efficiency at off load. Efficiency at off load. Efficiency at off load nothing but current off. Nothing but off into EI cos pi. Off into EI cos pi upon off into EI cos pi plus iron losses plus copper losses I square R losses of square into I square R. This is off-load copper losses. Or this can be written as off into kVA into power factor upon half into kVA into power factor plus iron losses plus half square into full load copper losses. This is off load copper losses and off load efficiency. As usually, if they ask you at any load, x load copper losses, x load copper losses is equals to x into EI cos pi upon x into EI cos pi plus iron losses. At any load, there is no changes in iron losses because these are perfectly constant losses independent of load. Plus x square into I square R losses. This is the efficiency at any load, x to load formula. For example, I want efficiency in terms of per unit values. For per unit values, the kVA is 1. 1 into power factor by 1 into power factor plus iron losses per unit plus copper losses per unit. This is the efficiency in terms of per unit. 1 into power factor because the kVA is taken as 1 per unit. kVA is taken as 1 per unit. For example, x load efficiency. X load efficiency is equals to x into power factor by x into power factor plus iron losses per unit plus copper losses per unit with x load. That's why x square into. This is at full load and this is at x load. These are the efficiency calculations. Simply how we can calculate the efficiency. Condition for maximum efficiency. We know that to get the maximum values? Differentiate the equation with respect to variable. So differentiate the equation with respect to variable. What is that? Differentiate the efficiency with respect to I, because when load changes, current changes. So EI cos pi upon EI cos pi plus iron losses plus I square R losses. This is what efficiency, and equals to 0. We have to do this. Differentiation of U by V. Differentiation of U by V is nothing but differentiation of V, or nothing but U. You can do anything here. So for example, U V dash minus V U dash by V square is equals to 0. U V dash minus V U dash by V square is equals to 0. Right? Like this. So do it. This is U V dash. What is V dash? EI cos pi differentiation with respect to I. Nothing but E cos pi plus, this is 0 because this is a constant, plus I square R, nothing but 2IR, minus V into V, nothing but EI cos pi plus WI plus I square R, V into U dash. What is U dash with respect to I? EI cos pi can be written as E cos pi by V square nothing but EI cos pi plus iron losses plus I square R losses whole square is equals to 0. Bring this one here. If bring this one here, the totally is equals to 0. And bring this negative term outside the equal. When this bring a negative term outside the equal, then it is positive. Now this is the final equation here. This is our final equation here. Now simplify this equation. E cos pi cancelled out each other. Now multiply on left hand side and right hand side. See what happened here. See, EI cos pi plus 2I square R is equals to this side EI cos pi plus iron losses plus I square R. EI cos pi gets cancelled out. Here 2I square R is there. Here only 1I square R is there. Bring this one here, so we can get I square R. 2I square R minus I square R. We can get 1I square R is equals to iron losses. So what is the condition to get the maximum efficiency? Iron losses is equals to, or exactly do as usually, copper losses is equals to iron losses. Copper losses is equals to iron losses, or iron losses is equals to copper losses. This is the condition to get the maximum efficiency. This is also written as, for example, what is the condition? Iron losses is equals to copper losses, right? Yes. This is also written as constant losses is equals to variable losses. This is the condition for maximum efficiency for any electrical machine. If constant loss equal to variable losses, we can get the maximum efficiency. Otherwise, simply the iron losses is equal to copper losses is the condition for maximum efficiency of my transformer. This is the condition for maximum efficiency at full load, because this is a full load efficiency formula. Then what is the condition for maximum efficiency at X load? Tell me, what is the condition for maximum efficiency at X load? The condition is the iron losses is the same, but at X load, iron losses is same, but at X load, copper losses are X square times of the full load copper losses. X square times of the full load copper losses. This is the condition for maximum efficiency at X load. Based on this, they are asking very important questions in all competitive exams. Tell me, at what load we can get maximum efficiency? Nothing but we have to calculate X value. So tell me, we know that iron losses is equals to X square times of the copper losses. From this, X square is equals to iron losses upon copper losses. From this, X is equals to square root of iron losses by copper losses. At what load we can get the maximum efficiency? At what load we can get the maximum efficiency? X is equals to square root of iron losses by copper losses. This is the X or load to get the maximum efficiency. They will give you, for example, my iron losses are 1000 watts, full load copper losses are 4000 watts. Then tell me, at what load we can get the maximum efficiency? If they ask you a question, at what load we can get the maximum efficiency? X is equal to square root of iron losses upon full load copper losses. So the answer is 1 by 2. So at half load we can get the maximum efficiency. At half load we can get the maximum efficiency. Like that we can get the answer. For example, if they given my full load copper losses are 3000. Now tell me, at what load we can get the maximum efficiency? At what load? Nothing but 4000 by 3000. Nothing but 1 by root 3. 1 by root 3 is nothing but 57.7% of load. At 57.7% of load, we can get the maximum efficiency. Like that, we have to calculate at what load we can get the maximum efficiency. And next question they are asking. Next question in competitive exams. At what load kVA we can get maximum efficiency? If they ask you a question like that, at what load kVA we can get maximum efficiency is nothing but same as usually, same like this. Here at what load kVA? At what load kVA? Nothing but full load kVA into square root of iron losses upon copper losses. At what load kVA we can get maximum efficiency? That is full load kVA into square root of iron losses by copper losses. Iron losses by copper losses at this kVA. Sir, here nothing is there, but here you write down that full load kVA. Why you didn't write here full load? At what load? At full load into square root. At what load kVA? Full load kVA into square root. Yeah, of course, here you have to write full load into half load, nothing but 1 by 2. Full load nothing but half load, nothing but 1 by 2. Full load nothing but 1. 1 into anything only. That's why no need to write here full load into, because we know the full load is nothing but 1. That's why I am not writing here full load into. But here full load kVA maybe 100 kVA or 300 kVA or 600 kVA or 500 kVA, we don't know exactly. But full load nothing but 1. Half load nothing but 1 by 2, like that. So at what load we can get the maximum efficiency? X is equal to square root of iron losses by copper losses. At what load kVA we can get the maximum efficiency? Full load kVA into square root of iron losses by copper losses. This is the condition for maximum efficiency and different questions. Generally, the condition for maximum efficiency is iron losses is equals to copper losses, or constant losses is equals to variable losses. But at x load, iron losses is equal to x square times of the copper losses. At x load, iron losses is equal to x square times of the copper losses is the formula. Now, take a graph. This is load and this is efficiency. This is at no load and this is at short circuited condition. This is open circuit condition. At no load, we have only iron losses. At short circuit condition, we have only short circuit losses. When load increases, iron losses, when load increases like this, iron losses constant, but copper losses increases. Iron losses constant, copper losses increases. Here, iron losses fully and copper losses zero. Here, mostly iron short circuited, that's why. At short circuit condition, this is zero and that is short circuit losses. But at some time, iron losses is equals to copper losses. At particular time, iron losses is equals to copper losses. At that particular time, we can get the maximum efficiency. When the iron losses is equals to copper losses, when we can get that one, where x is equal to iron losses by copper losses, at this x value, the iron losses and copper losses both are equal. At that condition, we can get the maximum efficiency. At this condition, iron losses greater than copper losses. At this condition, copper losses greater than iron losses. But at this condition, iron losses is equals to copper losses, then we can get the maximum efficiency. Right? So here, condition for maximum efficiency. Condition for maximum efficiency at x load. At what load we can get the maximum efficiency? At what load kVA we can get the maximum efficiency? We know all these questions and answers. When you went for exam, they will ask you another question. At which condition we can get the maximum efficiency? At which condition? Option A, pure lagging load. Option B, leading load. Option C, unity power factor. Option D, we can't say. In which of the following condition we can get the maximum efficiency? If they ask you a question like this, in terms of power factor, load is constant. In terms of power factor, at what magnitude of load is constant, but at which power factor we can get the maximum efficiency? If they ask you a question at unity power factor, you can get the maximum efficiency. At unity power factor, you can get the maximum efficiency when the magnitude of load is constant. If they want to magnitude of load to get the maximum efficiency, you have to calculate x is equal to square root of iron losses by copper losses. So simply here two conditions. Condition for maximum efficiency, copper losses is equal to iron losses, and condition for maximum efficiency, it should be works at unity power factor. So maximum efficiency occurs at unity power factor for your transformer. Unity power factor. Right? Is it okay? Now, very tricky question. Now see. Which of the following is correct answer? Voltage regulation at zero point 0.8 lagging is equals to voltage regulation at zero point 0.8 leading. Option B. Efficiency at zero point 0.8 lagging is equals to efficiency at zero point 0.8 leading. Option C. Both correct. Both correct. Option D. Both wrong. Both wrong. Now tell me, which of the following is correct answer? Option A, B, C, D. Which of the following is correct answer? I given you the regulation curve. I given you regulation curve. How the regulation curve? Generally, the regulation curve is like this. For example, here 0.8 lagging and here 0.8 leading. See here, at 0.8 lagging, voltage regulation is positive, of course. At 0.8 leading, voltage regulation is negative, of course. But the voltage regulation magnitude is high in lagging load, less in leading load. Always the voltage regulation for same power factors in lagging and leading. If you take same power factor lagging and leading, the voltage regulation in lagging is greater than leading. Always, for example, voltage regulation at 0.6 leading, voltage regulation at 0.6 lagging. Now tell me, equal or greater than or less than or none of the above? Which is correct answer? Equal or greater than or less than? Always in lagging, voltage regulation is greater than the leading. Always in lagging, voltage regulation is greater than the leading for same power factors. But the efficiency is same for lagging and leading loads. The efficiency at 0.6 leading is equals to efficiency 0.6 lagging. Efficiency at 0.6 leading is equals to efficiency at 0.6 lagging. Efficiency is same for same power factors, but the voltage regulation is not same. Always the voltage regulation is higher for lagging loads. Higher for lagging loads. This is simply the efficiency calculations. Very, very, very important. Okay, right? Understood? Very good. Thank you. Thank you, sir.